This is a new and improved version of my previously posted digital clock. It is built around an Arduino and uses a 20 columns by 4 rows I2C LCD panel instead of 16 by 2 LCD. Since this display has more columns and rows, it can show some additional information, such as the year and the day of the week. I have replaced the 24-hour format with the 12-hour format, including AM and PM indicators for a more familiar appearance. In addition, this is a perpetual clock, programmed to accurately follow the Gregorian calendar. It automatically adjusts for months with 30 and 31 days and accounts for the 4-year leap year cycle, requiring no manual correction to maintain accurate date tracking from the year 2025 through 2100. The circuit is simple. The serial data SDA and the serial clock SCL pins of the LCD are connected to A4 and A5 pins of the Arduino respectively. Contact pins of the set resume, up and down push buttons are connected to input pins 2, 3 and 4 of the Arduino respectively. Now you can see that the clock is displaying a future date and time. The current year shown is 2027, which is not a leap year. In a few seconds, the clock will pass through midnight. Since the date is December 31st, you will observe how the clock transitions to January 1st, 2028, which is a leap year. Now, we're going to set the clock to a set of desired values. First, press the Set Resume button once. You can see the hour digits are starting to flash. So at first, we are allowed to change the digits of the hour. Press and hold the Up button. The values in the hour digits increase. If you press and hold the Down button, the values decrease. Up, again, will increase the values. Now press the Set Resume button for the second time. This time, the minute digits are starting to flash, so you can adjust the minutes. Again, the Up button will increase, and the Down button will decrease the values. If the Set Resume button is pressed for the third time, it allows to change the digits of years, but we are going to keep the year as 2028. If the Set Resume button is pressed for the fourth time, the month can be changed, and we are going to change the value to show the February month. Only at last the date is allowed to change by pressing the Set button for the fifth time. Now, the year 2028 is a leap year, so we must be allowed to set the last date of the February month to 29. We'll check whether the program allows it. At the same time as we change the date, the day of the week changes automatically to the appropriate values. Remember, we don't need and we are not allowed to change the day of the week. The program will look after that. So, we have set the clock with our desired values. Now, if we press the Set Resume button for the last 6th time, the clock will resume and the second will be set to 0. The most part of the code is the same as in my previous digital clock project. The link to my previous video is given so the full detailed description can be found there. Here I am going to highlight the only portions which I have altered or amended. The library for the LCD is included. This project is simulated in Wokwi, and Wokwi simulates the Hitachi HD 44780UA00 variant, of which the address is 27 in hexadecimal. If you have an intention to make a real clock using actual electronic components, pay attention to the LCD panel that you are going to use and refer its datasheet to check the address it uses. This day index is a new variable which is used to pick the day of the week from the character array days. Note that the last day for the month of February is given as 28, which is used for ordinary years. For leap years, it should be 29, which will be looked after by the code. These hour underline 24 and meridian are also new variables. The values of the hour underline 24 vary with the values of hour. The string variable meridian will have either AM or PM string. The hour underline 24 is responsible to swap the string from AM to PM and PM to AM at noon and midnight, respectively. Since the digits to display hour and minute are 3 columns wide and 2 rows tall, customized LCD segments are defined in 8 binary arrays. But here in the code, hexadecimal numbers are used instead of binary numbers. The defined 8 binary arrays for the segments are then stored in the random access memory of the LCD. There are 10 void functions called display0, display1, display2, and so on to switch on the appropriate segments to display the digits 0 to 9, respectively, at specified columns. This section belongs to another function called selectDisplay. It is invoked from a different part of the program, which determines which digit of the hour or minute should appear and in which column. Once this information is received, this selectDisplay function then calls the display function to activate the appropriate LCD segments to show the digit in the specified column. This section introduces a new part of the project. As mentioned earlier, the time is displayed in a 12-hour format instead of the 24-hour format. When the hour value is between 1 and 9, the program treats 0 as the most significant digit. However, this leading 0 should not be shown on the display. This part of the code ensures that such zeros are omitted. This is an important new function in the project that returns the day of the week for any given date in the Gregorian calendar, based on the provided year and month. It uses Sakamoto's algorithm, which is compact, efficient, and well suited for computer implementation. This void function, named setResume button pressed, is triggered when the setResume push button is pressed for the first time. A while loop is used to track how many times the button has been pressed. On the first press, the program flow is directed to a routine that handles the hour setting. When the button is pressed a second time, control moves to a routine that sets the minutes. In the same way, subsequent presses allow the user to set the year, month, and day. On the sixth press, the function completes its execution by setting the seconds to 0 and exiting. This is the main void loop function, and this part checks whether the setResume push button is pressed. If the button is pressed, the clock will stop and the setResume button pressed routine will be invoked. Each time the main void function executes its loop, the value of the variable second is incremented by 1. At the beginning of the loop, the program checks whether second exceeds 59. If it does, second is reset to 0 and minute is increased by 1. Similarly, if minute exceeds 59, it is reset to 0 and hour is incremented by 1. At the same time, the variable hour24 is also incremented by 1. If hour exceeds 12, it is reset to 1. When hour24 equals 12, the meridian is set to PM. If hour24 reaches 24, it is reset to 0, the meridian changes to AM, and the date is increased by 1. After the date is increased by 1, a couple of other variables are checked as well. In line 296, last date of the current month is fetched from the array last date and stored in a variable named last date to check. For the month of February, 28 is the number stored in the array, but if the current year is a leap one, this should be 29. Now, look at the underlined condition in line 297. This checks whether the current year is a leap year. If so, and if the month is February, number 29 is stored in the variable last date to check. Then, in line 300, the date is checked to see whether it exceeds the last date of the current month. If so, the date is reset to 1, and the month index is increased by 1. If the month index exceeds 12, it is reset again to 1, and the year is increased by 1. At last, if the year exceeds 2100, it is reset again to 2100.
This part of the code evaluates the most and the least significant figures of the hours and minutes and assign appropriate column numbers to display. Line 325 is a new one, which displays the correct meridian, AM or PM. This portion is responsible to print the digits of second and year at correct columns. Line 341 checks whether the current year is leap year, and if so, the word leap is displayed just below the digits of the year. This is the last part of the void loop function. The date and month are displayed. The line 354 calls the function day of week, which consists the Sakamoto's algorithm to fetch the correct day of the week, and line 355 prints that day. As you know, a pair of flashing symbols appears between the hour and minute digits to indicate that the clock is running. The lines from 357 to 367 create this flashing effect. The symbols remain visible for 500 milliseconds and then disappear for another 500 milliseconds. The delay functions in lines 362 and 367 control these durations. Because of this, the clock effectively pauses for 1 second before the second variable is incremented by 1 in line 370. However, if the clock runs slightly slow or fast due to external factors, you can adjust the delay durations by increasing or decreasing the millisecond values in these delay functions accordingly.
As discussed earlier, when the Set Resume push button is pressed for the first time, a routine named Set Resume Button Pressed is executed. This routine keeps track of how many times the button has been pressed and, based on that count, directs the program flow to adjust the hour, minute, year, month, or date. The routines that handle these adjustments are defined here. For instance, when the button is pressed for the first time, control is passed to this setting hour-minute routine.
The lines from 374 to 392 create the flashing effect for the hour digits and the meridian indicator. Lines 394 to 429 handle the increment or decrement of the hour digits, depending on whether the up or down push button is pressed. The same operation is performed for the minute, year, month, and date displays in the remaining sections of the code.
Thank you for watching this demonstration. I hope you found it interesting and learned something new. If you enjoyed the video, please give it a like and share it with others who might find it useful. I'd love to hear your thoughts, so feel free to leave your questions or comments below. And if you'd like to see more science content like this, don't forget to subscribe and hit the notification bell so you won't miss future videos. Thanks again for your support, and see you in the next demonstration.